Hello everyone, my name is Anastaiya Chernikova and I will continue the talk about LLVM-snippy. In the first part, Konstantin told you about the generator itself, how it is built, why we built it on top of LLVM, how instruction histograms are specified, memory handling, control flow, and the other generation mechanisms. My part will be more about the practical use of this tool in a real verification scenario. We took the open source RISC-V core Ibex and tried to answer a few questions. First, how easily LLVM-snippy can be embedded into an existing verification infrastructure. Second, which generation scenarios actually help to achieve full coverage. And third, what this approach gives in practical, what coverage we managed to reach and what changes we needed in the Ibex infrastructure. So from here on, things change a bit. We are no longer looking at LLVM-snippy as a standalone generator. What we really care about now is how it behaves inside the complete verification environment. Let's talk in more detail about what the core itself consists of. Ibex is an open source 32-bit RISC-V core. It is compact, but it still has all the functionality you need. It supports the base RVCT2I and E configurations, the M extension, and part of the bitmanip compressed extensions. ZCB and ZCMP are supported experimentally. The core also fairly mature blocks such as CSR, PMP, support for physical memory protection mechanisms, and debug logic. On the diagram, to the right, you can see the core's main structure. Instruction fetch, decode, and execute to write back the register file, the LSU for memory access, the CSR block, and the execution units, including the ALU. So this is not just a minimal interpreter of RISC-V instructions, but a full processor core with a pipeline and a set of additional mechanisms that matter for real-world use in microcontrollers. Why Ibex in particular? First, this is well suited for demonstrating different types of coverage. There is ordinary instruction execution, memory access, a pipeline, hazard scenarios, CSR, and privilege mechanisms. In other words, it is a good testing ground. On it you can see not only did the add instruction execute, but also whether the test truly makes the core behave in varied way. Let's assume we already have a written processor core. The next question is how do we make sure it actually works correctly? The core itself can only execute instructions. That is why a test bench is built around it, taking care of everything else. It drives the core's clock and resets signals, models the memory, loads the test programs into it, and compares the core's behavior against a reference model. But simply running the test is only half the job. Even if all the tests pass, we still needed to understand what exactly we have checked. Cover groups are responsible for this. They watch the situation we care about, whether every register has been exercised, whether positive and negative values have come up, whether dependencies between neighboring instructions, hazards, have been checked. From the simulation logs, cover groups accumulate statistics and report the coverage percentage, clearly highlighting the places that have not yet been checked. And here Ibex turns out to be convenient a second time. A fairly divided coverage model has already been written for it. It consists about 5,000 cover points, and this is an important point. We don't just run the test and consider the job done because they passed. We have a large number of cover points that let us understand in fair detail which scenarios the core actually went through. The diagram shows that coverage is roughly divided in two large parts, unprivileged and privileged. In the unprivileged part, ordinary instructions execution is covered opcode, RVST2I instructions, compressed instructions, illegal and hidden codings, operand and register combinations. Instruction classes are covered separately. Arithmetic, logic, load, store, branch jump, and system instructions. But the most interesting part begins at the microarchitectural level. There matters not simply whether the instruction executed, but how exactly it passed through the core. Through fetch, decode, write back, whether there were stalls, hazards, branch outcomes, pipe flushes, memory responses. A simple linear test quickly stops being enough here. On the right of the diagram is the privilege coverage. CSR, privilege mode, debug, interrupt, PMP. This is an important part of Ibex. But in our case, there is a limitation. LLVM-snippy is mainly aimed at the unprivileged ISA. So we will consider the privilege cover groups separately later and exclude some of them from the analysis. The task can therefore be formulated as follows. Take a tool that is good at generated random instruction sequences and check how much of such a rich coverage model it can close. Another reason we chose Ibex specifically is that it already has a ready-made verification environment built on riscv-dv. With core build, RTL simulation, ISS co-simulation, join execution with an instruction set simulator, and coverage collection. riscv-dv is an open source generation of riscv test programs. It is written in System Verilog UVM and fits naturally into an RTL verification flow. The general idea is this. First, riscv-dv generates a random but valid riscv program. At the same time, you can configure which instructions to use, which mods to engage, and which scenarios you want to obtain. Machine, supervisor, user, and debug modes are supported, so you can check not only ordinary instruction execution, but also more system-level scenarios. Next, this program is built into an executable image and run as a pair. On the one side, the RTL model of the Ibex, on the other, a reference ISS model. After execution, the results are compared. In the behavior on the RTL and the ISS diverges, then there is a problem somewhere, either in the core or in the test environment or in the test assumptions. And on the top of all of this, functional and code coverage are collected. So riscv-dv here gives not just a set of random programs, but a full verification flow, test generation, build, run, comparison against the model, and coverage analysis. So for Ibex, this is a very strong starting position. We already have a working infrastructure and a clear baseline to build from. Now that the baseline is clear, the next question is, how do we carefully add a new source of tests to the existing infrastructure without breaking the whole flow? The idea here is quite practical. We don't want to rewrite the Ibex environment from scratch. We already have a test bench, an RTL build, a co-simulation run, and coverage collection. So it is logical to replace only the source of the test program and leave the rest of the infrastructure in place. That is, instead of having the program generated only by riscv-dv, we add the ability to plug the tests created by LLVM-snippy. As a result, the flow looks like this. LLVM-snippy generates RISC-V code, then the code is built into an executable image and run inside the existing Ibex environment. And the rest, co-simulation and coverage collection, stays in the same. This is convenient for two reasons. First, we can use the strengths of the already finished flow. We don't need to solve the questions of initialization, core startup, result handling, and coverage all over again. We simply add one more way to generate a meaningful program. Second, we compare the tools under identical conditions. If the coverage changes, we know it is due precisely to the characters of the generated tests and not because we change the half of the infrastructure. But there is an important limitation. LLVM-snippy is primarily aimed at generating tests for the unprivileged part of the ISA. So the privileged cover groups we spoke about earlier will be excluded from the analysis going forward. And from here on, we will focus on how well to remaining coverage can be closed through the generation of random sequences. So the experiment is set up like this. We take the existing Ibex infrastructure flow and carefully embed LLVM-snippy into it. Let's start examining the first modified stage of the existing pipeline. What kind of tests riscv-dv should now generate? Here is important to understand. We no longer need an ordinary riscv-dv test in which the whole instruction stream is generated by itself. Instead, we need a special wrapper that can hand control over the code generated by LLVM-snippy. How do we make riscv-dv generate a wrapper that calls the function we need while not corrupting the register state? For runs with LLVM-snippy, riscv-dv generates not an ordinary random instruction stream, but a single wraparound SnippyFunction. This wrapper is created once and then reused for any number of LLVM-snippy tests. This job is to safely hand control over the generated code and then return to the standard riscv-dv flow and reach test done. The test itself is built on top of riscv inster-based test, so we stay within the standard structure of riscv-dv tests. But we change its substantive part. By overriding the generate inster stream function instead of a random instruction sequences, riscv-dv generates a template that calls SnippyFunction. And here a key requirement immediately appears to pre-save the state before the call. Before entering SnippyFunction, the wrapper saves all registers onto the stack and after execution restores them completely. This matters precisely because LLVM-snippy is a random generator. It produces code and knows nothing about the external riscv-dv wrapper that calls it. From LLVM-snippy's point of view, all available registers are scratch registers, and it can use them however it needs to build the test. So the external environment must not count on any values being preserved by chance. The stack pointer is handled separately. Its value is written into global memory and then restored from there. This is needed because the stack may also be used inside the SnippyFunction, for example, to call internal functions. As a result, riscv-dv is responsible for correctly entering and leaving the LLVM-snippy code, while the generated code itself stays instead the function produced by LLVM-snippy. Once the wrapper is generated, the next task is to embed into the overall Ibex run. The diagram shows two code sources. riscv-dv generates the environment and the call to SnippyFunction, while LLVM-snippy generates the main random instruction sequences. But the simulation cannot work with a set of separate files. It needs a single executable image that both the RTL and the simulator interpret in the same way. At this point, the next integration step appears, combined linking. We needed to merge the riscv-dv and LLVM-snippy code, keep the memory regions separate, and preserve the expected layout for code, data, and stack. Otherwise, the generated test may be valid by itself, but invalid inside the Ibex run. Well, let's look at how the combined linking is arranged in practice. Each LLVM-snippy test uses a sections.yaml file in its config. It defines the memory map for the generated fragment, where code, data, and stack should be placed. Based on this information, LLVM-snippy generates its own linker script. But this is not enough for the final ELF because it must also contain the riscv-dv part, startup code, the wrapper, service regions, and everything needed to run in the Ibex environment. So Ibex adds a combined linker script, snippylinker.elf.ld. It describes the riscv-dv sections, while the linker script generated by LLVM-snippy is included via include. As a result, both parts are assembled into one executable image, but each remains in its predefined memory region. Now let's look at what this linking produces in the final ELF file. Here is the list of sections after the build. It shows that riscv-dv and LLVM-snippy are placed in one executable image, but their regions are not mixed. The ELF starts with the usual riscv-dv sections: text, data, service regions, user stack, and kernel stack. They are needed for startup code, the wrapper, handlers, and test completion. Then the LLVM-snippy sections flow: text, data, and stack, each with its own access rights. As a result, the LLVM-snippy code, data, and stack remain separated from the riscv-dv environment and from each other. This confirms that the combined linker script produces a single ELF with a predictable memory layout, which is important both for correct execution and for debugging. With that, the first part of the integration is complete. We now have a riscv-dv wrapper that can call LLVM-snippy code, and both parts are merged into one executable image with a predictable memory layout. Now we can move to the main question. What does this integration give us in terms of coverage, and which scenarios are worth adding first? From here we start experimenting. We take different generation scenarios, run them in the Ibex flow, and observe how the coverage model responds. Let's start with the simplest scenario. For now, we don't add complex control flow, special corner case, or directed dependencies. First, we want to understand the baseline. What LLVM-snippy can cover almost out of the box if we only ask it to generate an ordinary instruction sequences. For this, we take the arithmetic and logic instructions, add, a die, and similar operations. In the config, we set the RV32IMC architecture with bitmanip extensions and generate 10,000 instructions. The test is intentionally simple. No branches, no loops, no function calls, no active memory access activity. It is just a linear instruction stream aimed mainly at instruction level coverage. At this stage, we don't try to close everything. This is a starting point. First, we see how far the most basic LLVM-snippy test gets us, and then we analyze what is missing. We run this basic arithmetic test 3 times and look at the coverage. The result is predictable. Even this simple linear scenario already close mainly cover groups. It executes different instructions with different registers and operands, so opcode and basic operand cover points fill up quickly. But the limitation is also clear. A linear arithmetic test almost does not affect execution flow. It has no conditional branches, loops, or functional calls. It also creates a little pipeline stress. Instructions come one after another and without direct dependencies, many microarchitectural scenarios appears rarely. Hazards, stalls, flushes, and so on. So the first experiment shows two things. LLVM-snippy quickly gives coverage across the instruction space, but one large linear stream is not enough. To go further, we need to control not only which instructions are generated, but also how they interact. Let's open the coverage report and see what stands behind these numbers. First, we look at the overall summary. There are several coverage types here, and it is important not to mix them up. Line coverage shows which RTL line were excluded during simulation. For such a simple test, the result is fairly good. The core executes instructions and goes through fetch, decode, execute, write back the register file and the ALU. But highline coverage does not yet mean that we checked the interesting behavior of the core. Toggle coverage shows how actively internal signals switched. Here it is already clear that the test is monotonic. The arithmetic stream gives a lot of execution, but does not often change operation modes, enter different states, or actively work with memory or branches. PSM coverage shows states and transitions of finite state mechanics. It stays low because the basic test has almost no exceptions, active stalls, or transitions that could lead to flushes. Branch coverage here means branches in RTL code, such as if and case statements, not RISC-V branches instructions directly. Again, the limitation of the linear test is visible. We execute instructions, but we don't force the RTL through mean alternative passes. Finally, group coverage is the most relevant for us. This is where the Ibex cover groups leave opcode registers, immediate values, hazard scenarios, load, store behavior, branch history, and microarchitectural states. In the groups list, we can see the picture is very clear. Arithmetic and logic instruction level groups close well because they are exactly the instructions from the histogram. But the groups related to control transfer instructions still have empty spots. For example, the add group shows that the basic arithmetic test does its job. The RS1, RS2, and RD registers, operands, signs, sign cross, and GPR hazard are covered. So for ordinary arithmetic instructions, LLVM-snippy quickly cycles through different registers and values. But this is only one instruction classes. It does not mean that the core behavior as a whole covered. The same report immediately shows where the linear test is well. Now let's look at branches cover group. For example, BQ and then B and E, we see the difference is immediate. BQ covers only part of registers and combinations, and then we can see the B and E instruction may even stay at 0 at all positions. This is expected because branches are not the main scenario in the basic arithmetic test. Another useful example is branch hit history CG. At the first glance, the outer bins look puzzling, but the meaning is simple. They represented different values of the branch history cover point. The CP branch history available encodings branch outcomes. Since the bins go from 0 to 31, they correspond to different taken, not taken patterns, roughly like a 5-bit history of recent branches. Only 4 from 32 bins are covered. The basic test accidentally hints a few branch history patterns, but does not check them systematically. The conclusion is important. For branch coverage, taking a branch once is not enough. The cover group expects different histories of taken and not taken outcomes, so we need sequences of branches, loops, and different control flow patterns. That is why the next tests use a more controlled structure, the control flow graph. So the coverage report works as a map for the next step. It does not just say coverage is 68%. It shows which scenario classes are missing. Let's start with dependencies between neighboring instructions. A clear example is the RAW hazard, read after write. The first instruction writes a result to a register and the next instruction immediately reads the same register as a source operand. For the pipeline, this is more interesting than two independent instructions. The core must handle the dependency correctly, either through forwarding or through a stall. Read after write is only one example. The coverage model may include different hazard scenarios, and what matters is not just one dependency somewhere in the test, but such cases for all relevant instructions from the histogram. LLVM-snippy can generate the needed sequence by chance, and the code fragment on the right shows that this can happen. But as the number of instructions, registers, and dependencies grows, the space of combinations grows quickly, and relying on the variable random seed is not reliable. So, before writing a hazard-oriented test, it is useful to estimate how many instructions we need to cover all read after write scenarios of interest with high probability. Next, we compare this theoretical estimate with actual run results. Now let's estimate this probability. For the experiment, we take a small set of instructions with one source operand. You can see the list of them at the bottom of the slide. The task is to generate a test and check whether a read after write hazard occurred for each instruction in this set. We need coverage not just of one dependency somewhere, but of all operations from the histogram. In the formula on the slide, n is the number of generated instructions, m is the number of instructions in the histogram, and r is the number of available registers. The intuition is simple. More instructions increase the chance of dependencies, while more operands and more registers make it harder to hit all combinations by chance. We check this in practice. We run the same scenario with num insters from 0 to 105,000 in steps on 100. For each value, we did 25 runs and measure the function of runs where read after write was covered for all 6 instructions at once. The graph shows that the experimental points closely follow the theoretical curve. This is useful because it connects a coverage problem with a simple probability model. We can estimate the required test size instead of guessing it. The practical conclusion is also clear. If we rely only on randomness, the required test lengths can become large, especially when many registers are available and neighboring dependencies appear less often. So for hazard coverage, we should not only generate more instructions, we should also control the probability of dependencies. One simple way is to limit the number of available registers. This is exactly what we do in the basic coverage scenario. We limit available registers or memory regions so that interesting scenarios do not have to appear only by chance or only with a lucky seed. The slide shows two techniques based on this idea. The first one targets register hazards. We take roughly the same arithmetic and logic instructions, but restrict the list of available registers through reserved flag list. Then the generator has fewer independent registers to choose from and dependency chains appear more often. Instead of independent instructions with few dependencies, we get chains where one instruction computes a value, the next one immediately uses it, and the third one uses the result of the second. This is already more interesting for the pipeline. The second technique targets memory hazards. The idea is similar. We limit the memory region with large memory area access spread across the address space. With a small data section, load store instructions more often access neighboring or identical addresses. In addition, init memory full is enabled so memory is properly initialized and load store scenarios can be generated actively. This is controlled randomness we set useful boundaries and the generator still finds varied options inside them. In other words, we don't hardcore the final instruction stream, but we make the interesting situations much more likely. Dependencies between registers and memory are not enough. To push coverage further, the program must change the execution flow. We add branches, loops, and function calls. This slide shows three scenarios. The first one is loops. We set loop ratio 1, so branches are used specifically to form loops. At the same time, we limit nesting depth, so the test remains interesting without creating excessively long repetitive loops. The second scenario is conditional forward branches without loops. Here we set loop ratio 0. Such a test exercises branch instructions and chance in control flow, but without jumping back. The third scenario is function calls via a call graph. We explicitly describe which functions may call one another, and LLVM-snippy generates a program with such transitions. This covers not only conditional branches, but also jump, call, return behavior. This matters because branches directly affect the pipeline, taken or not taken, flushes, and transactions between basic blocks. We start checking not only what is executed, but also which path leads to it. After the linear arithmetic test, this is an important step. The program becomes a struct execution graph instead of a straight instruction stream. The next source of interesting scenarios is memory access behavior. Simply adding load store instructions to the histogram is not enough. Such a test is valid but often too regular. Before each memory access, the generator inserts helper instructions to form the address and then performs on load or store. For coverage, this is not always the best pattern. We want to exercise the LSU more intensively and obtain sequences where memory access go one after another. For this, LLVM-snippy has burst mode. Address preparation is hoisting up and then load store operations are performed back to back and as a burst. This stresses the memory subsystem much better. Addresses can also be controlled through access ranges, range, stride, and offset. For example, first offset and last offset can be chosen so that misaligned access appear almost immediately instead of by chance. We give the generator constraints under which the needed memory pattern appears naturally and remains reproducible across runs. Another interesting scenario is self-modifying code. So far we changed how the program executes, dependencies, branches, and dense memory access. Here the program changes its own instructions during execution. LLVM-snippy can generate such tests via SMC-gram. It does not just write random bytes into the code region. It guarantees that after writing, there is still a valid executable instruction. In the example on the right, one instruction first executes at the given address, then the code is rewritten and another instruction appears at the same address. For the core, this is more complex than ordinary sequential execution of a known text. Such text are useful for instruction side logic, fetch, prefetch, possible catching effects, and rewriting an instruction after it has been changed. So this is another way to make the core go through a more unusual execution path, not just more instructions. Now let's look at the result after the basic set of scenarios. This is no longer one arithmetic test, but several scenario classes. Instruction dependencies, memory hazards, branch loops, function calls, burst mode, misaligned access, and self-modifying code. This set already improves coverage noticeably. The program is no longer linear and exercises memory, pipeline, and control flow more actively. It also creates more combinations between instruction classes and internal case states, which is exactly what the microarchitectural coverage needs. But specific kernel case still remain. Special operand values, special registers, and RAID combinations that are hard to catch with ordinary random generation. Next, we will target exactly those scenarios. Now let's look at the coverage report after running the whole basic set. On the dartboard, the main difference from the first arithmetic run is clear. Group coverage grew to roughly 88% and line coverage to roughly 81%. So we did not simply add more instructions, we added different types of program behavior. Let's start with a load instruction. For example, LWCG. This group closed on 100%. It covers not only execution of the instruction, but also RS1 and RD values, immediate sign, GPR hazard, LSU hazard, and access alignment. This is the result of memory tests. We added load store instructions, limited the memory region, used a small data section, and access ranges. So the LSU receives denser and more varied access. Now let's look at branch hit history CG. In the first arithmetic run, this group was almost empty, but after the basic branch test, it closed completely. Now let's look at the jump groups. JAL CG and then for JAL CG. The cover is much better than after the linear test, but still not perfect. For JAL, immediate signs and alignment are covered, but not all RD variants. For JALer CG, some combinations of RD, link registers, and alignment remain uncovered. So the basic call graph helps, but fully closing jump scenarios needs more precise settings. Which registers to use and return address, how to place functions in memory, and how to obtain the required offset and alignment combinations. For a store instruction, for example SWCG, the picture is almost fully closed. RS1 and RS2 immediate sign, GPR hazards, LSU hazard, and misaligned are covered. At the same time, one uncovered bin may remain. Related to X0, the source register that leads to the next specific scenario, same x0 cases are hard to obtain by chance and needed to a separate test. The next example is diffcg and then ramcg. They're the same. At the first glance, coverage is good. Registers, operands, signs, and hazard coverage. But inside CP-diff result, diff overflow is still not covered. This is expected. Division overflow is a rare case, 1 in 2 in the 64th. It requires exact operands, the minimum negative number and -1. Random generation may not hit the combination for a long time, even if the rest of the instruction group is already well covered. Another uncovered group is illegal compressed instructions. After the basic set, it stays at 0. This is normal. Basic tests generate valid executable code. They should not accidentally insert illegal encodings because then execution would go to the trap handler and change the whole execution flow. But the Ibex coverage model still needs these scenarios. So legal instruction must be checked with a separate directed test where we deliberately invoke the needed opcodes and return correctly from the handler. A similar situation appears with CSR groups. After basic unprivileged scenarios, they stay uncovered or weakly covered. This is also expected. LLVM-snippy mainly generates unprivileged instructions, while CSR is closer to the privileged part. Such groups needed separate configs. The conclusion after the basic set is this. Most coverage is closed, but rarer cases remain. So next we move from basic scenarios to specific ones. Instead of one expanding the histogram, we fix the needed values, registers, and generation conditions. Let's start with overflow for diff and rem. It requires specific operands. Replying on a random seed to hit this combination is not practical. Basic binary logic instructions have a similar issue. Interesting cases appear when the register value and the immediate consider or have opposite signs. For such situations, LLVM-snippy provides operands reinitialization. We do not rewrite the whole test by hand. We tell the generator that for certain instructions, these operands should something be substituted. This turns a rare corner case from a lucky event into a reproducible coverage scenario. The next target scenario is related to x0 and load store instructions. For arithmetic, x0 can naturally appear as an operand. But for load store, it is tricky. If x0 is used as the base register, the address is different only by the immediate. Since the load store immediate is limited, the scenario is possible only in a low memory region, roughly up to 1000. To cover it, we create a separate low address section, for example starting at 100, and reserve most registers. This makes it much easier for the generator to select x0 while staying within a varied address range. Again, we don't write specific instructions by hand. We create conditions where a rare cover point becomes reachable and reproducible, while the rest of the instruction stream is still generated automatically. Now let's move to another infrastructure change. So far we carefully assembled a combined ELF with the riscv-dv environment, LLVM-snippy code, data, and separate memory sections. But this image still needs to be loaded into the testbench memory. Here, a limitation of the standard riscv-dv flow become visible. The old loader simply took a binary file and wrote it into memory sequentially from a base address. In effect, the whole file was treated as a contiguous block of data. This was problematic for the X0 load store scenario because it related a low memory region before the start section. For LLVM-snippy scenarios, we have a full ELF layout, different sections, load addresses, and separate regions for code, data, and stack. If such an image is loaded in rows, the real section addresses are lost. Then the layout we set at linking time may not match the memory seen in simulation. So the Ibex flow had to load the ELF not as a float binary, but according to its real structure. Instead of writing bytes sequentially from one base address, the new loader looks at ELF segments and loads only those that must be present in memory, namely PT load segments. .bss is handled separately. If a region must exist in memory but has no data in the file, it is filled with zeros. This also ensures that memory is initialized identically for the RTL and the simulator, so both sides of the comparison start from the same initial state. This is important for co-simulation, otherwise a mismatch could come from loading, not from the core behavior itself. As a result, the ELF loader becomes not just metadata inside the file, but the actual layout used by the test. The next group of specific scenarios is control transfer instructions. We already exercised branches and jumps in the basic set, but for coverage the details often matter more than the transfer itself. For Jaller, CJaller, and CJR, LLVM-snippy can randomize the low bit on the source registers and the immediate. These details affect how the core handles the branch address. You can also control the return address register through redefine. By default, it is random, but it can be fixed, including separately for internal functions. Another important mechanism is code layout. It controls code placement and can produce, for example, negative branch offsets. Without it, such cases may appear inconsistently or miss the required cover points. Now let's move to the part we set aside at the beginning, privileged scenarios. LLVM-snippy does not close them fully, but some cases can still be covered in a targeted way. The first example is CSR instructions. What matters is not only generated instructions shown on the slide, but accessing a specific CSR register. In our case, we fixed status through imhist by setting the CSR address to 3000. The second example is interpret scenarios. Here the test must not conflict with the environment. For Ibex there is resolve x4 because the wrapper uses it for the kernel stack. whereby the generated code could club a state needed by the handler, and the failure would be caused by the harness, not by the instruction scenario. The third case is the legal instructions. It is easier to add them through an external assembler function and call it from generation code. This keeps the LLVM-snippy flow, but adds in a target way what the generation should not freely randomize while still running inside the same environment. The same approach can be used for other scenarios that are easier to close with a small assembly test. So for the privileged part, we can still target individual important cover points. For a break and illegal instruction scenarios, one more improvement was needed: the trap handlers. In the standard variant, the handler simply advanced EPC by 4 bytes. But for RISC-V, this is not always correct. Tests may contain 2-byte compressed instructions, ordinarily 4-byte instructions, and sometimes longer legal encodings. If we always increase the register by 4, execution may resume in the middle or an instruction or skip extra code. For an ordinary test, this immediately breaks the execution flow. So they break and the legal instruction handlers were overriding. Now they determine the actual length of the trapped instructions and advance MEPC by the correct value, 2, 4, 6 or 8 bytes. This is a small but important detail. Without it, some tests could not be properly being run in the Ibex flow. Let's look at the result of these specific scenarios. After the basic set, we had 88% functional coverage. By targeting rare cases, we brought it up to 100. Code coverage also improved slightly, line coverage increased about 1%, toggle about 3%, and branch approximately 1% improvement. These numbers are smaller, but they show that the specific tests also after RTL activity. This is a real very good result. According to the functional model, we closed everything planned for this test. But can we do better? Let's open the report and see what else can be improved. On the dashboard, you can see that group coverage is 100. Functional cover groups are closed, but toggle coverage is still around 78%, and branch coverage around 74%. So now we don't need to target a specific functional bin. We needed to understand which RTL bars still don't switch actively enough and which code branches are not taken. The model list shows that branches coverage is uneven. Some models still have noticeably incomplete branch coverage. So the remaining potential is not opcode coverage, but in more varied program behavior. PC changes, memory access distribution, offsets, alignments, and the mix of branches with memory access. Here we look at toggle coverage for Ibex top tracing. Some signals already switch, but some address bits stays almost consist. For example, upper bits of instruction address like this, upper current PC, next PC, exception PC, and last data adder. This means the test execute code and access memory, but within limits address regions. To raise toggle coverage, it makes sense to spread code and data across different memory ranges, so upper PC and data address bits change more often during the run. Now let's look at Ibex load store unit, especially branch coverage. Now all branches inside the LSU are covered. For example, some variants remain in byte enable sections by access type and offset. A simple issue appears is sign extension for bytes and half-word loads. Some contributes of offset and signed unsigned access have not occurred. So the LSU is functionally covered, but RTL branches still require denser memory scenarios. Different load store sizes, offset, aligned and misaligned access, and different memory regions. This is a good example of the gap between functional coverage and the code coverage. This motivates the stress test. Its goal is not to close a new functional cover group, but to exercise the RTL header. Mix LU, M extension, bitmanip, compressed instructions, branches, calls, and active load store access to different addresses. Such a test should change PC and data addresses more often, switch signals more actively, and pass through more branches in LSU, fetch decode, and control flow logic. To close the missing cover points, we built a stress test by combining the ideas from previous scenarios in one config. Code and data are spread across different memory regions, so PC and address signals change more actively. For load store, manually access ranges are added, different regions, aligned and misaligned access, and different offsets. This gives the LSU denser and more varied traffic. The program itself is also mixed. Load store branches, jumps, LU, compressed instructions, M extension, and bitmanip all appear together. This is closer to a realistic stress stream than to a narrow directed test. So this is not a test for one corner case, but a standard program designed to change the course behavior more actively. Now let's look at the same report after adding the stress test. Group coverage stayed at 100, however toggle coverage grew noticeably 8% improvement. Branch coverage also rose slightly about 0.5%. Let's look again at Ibex top tracing. Before the stress test, some address bits barely switched. Upper bits of instruction address, current PC, next PC, and last data address stayed too stable. After that stress test, the picture is better. Address signals switch such more actively. This is what we expected. Code and data are used in more varied memory regions, and the program changes execution flow more often. So PC and data addresses stop being almost constant. Now let's look at Ibex load store unit. Before the stress test, uncovered branches remained in byte enable section, offsets, and sign extension for byte and half-word loads. Functionally, the load store groups were already closed, but not all RTL memory access combinations occurred. After the stress test, some of these places closed. For example, additional variants appear and byte access and sign extension at different offsets. This shows that the stress test really produced more varied memory scenarios. The takeaway is this: specific tests closed functional coverage, and the stress test helped shake up code coverage. It did not add a new cover group type but made familiar core mechanisms: page, PC update, LSU, and control flow work in a more saturated and mixed mode. The report shows that further scenario design can continue improving coverage in this direction. After coverage, one practical question remains. The tests work and coverage grows, but how fast are they generated? Here we compare the generation time for riscv-dv and LLVM-snippy. Only generation was measured, without RTL simulation or coverage collection. The test size varied from 1000 to 50,000 instructions in steps of 1000. For LLVM-snippy, the test environment was created once and reused between runs. The graph shows that LLVM-snippy generates tests noticeably faster. For riscv-dv, time grows more steeply and less consistently, while LLVM-snippy scaling is smooth across the whole measure range. This matters for CI. If test runs on every PR or in nightly regression, generation time affects the overall checking cost. Phase generation makes it easier to add more scenarios, run more seeds, and get coverage feedback sooner. Another step, riscv-dv test took about 29 hours single-threaded, while LLVM-snippy tests took about 2.5 hours. So LLVM-snippy is useful not only as a source on new scenarios, but also as a faster option for regular unprivileged ISA coverage runs. One more practical advantage is support for new extensions. Ibex is gaining support for compressed and bitmanip extensions, for example, ZBA and ZCMP. The generation must be able to produce these instructions and include them in scenarios. In riscv-dv, such extensions are not supported by default, so instructions descriptions are generation supported must be added separately. An example implementation is shown in the PR linked at the bottom of the slide. LLVM-snippy is convenient here because it relies on the LLVM target description. If an instruction is already described in LLVM, it can be used almost out of the box. We specify the needed march, add the instruction to the histogram, and build tests for the new core configurations. This applies not only to Ibex but to extensible riscv cores in general. When the ISA evolves, it is much better to reuse what already exists in LLVM than to manually update the generator every time. This reduces required support and makes new configurations available for testing earlier. Now let's look at the overall result when the regression includes both riscv-dv and LLVM-snippy. On the left is coverage without LLVM-snippy. The overall score is already high, around 91%, but some individual groups remain noticeably incomplete. After adding LLVM-snippy, these groups close consistently to 100%. So LLVM-snippy does not just slightly raise the overall percentage, it closes specific gaps that could remain uncovered in a riscv-dv regression. The overall group score rose by roughly 2%. After this glance, this may look small, but behind it are specific groups that now close fully and reproducibly. For coverage closure, this is exactly what matters. Not a likely one-off run, but stable closure and problematic cover groups even with random seeds. The final conclusion is that riscv-dv and LLVM-snippy are complementary tools. riscv-dv covers system and privilege scenarios, while LLVM-snippy helps close on privilege, instruction level, and microarchitectural coverage in a targeted way. Putting it all together, the APR adds to Ibex not just separate tests, but full LLVM-snippy support inside the existing DV flow. The first part integrates the generator itself. LLVM-snippy configs a CMake-based flow and the ability to run such tests through the standard Ibex DV mechanisms. The second part handles integration with riscv-dv, the special wrapper, the call to SnippyFunction, and combined linking that assembles the riscv-dv environment and LLVM-snippy code into one ELF. The third part adapts the infrastructure. We needed to rewrite the ELF loader so it loads segments at the real address and refine trap handlers so tests with the break and illegal instructions return reliably to the next instruction. Importantly, none of this change modifies the core RTL. The patch extends only the DV flow. It adds a new source of test programs, but runs them in the same UVM and Casim environment as the existing riscv-dv tests. As a result, LLVM-snippy tests can be used in a standard Ibex regression collection, combined coverage together with riscv-dv and the reduced test generation time. We have shown how LLVM-snippy can be embedded into the existing Ibex flow without rewriting the environment and how different generation scenarios can close coverage. To try the generator inside the Ibex or look at example configs, you can follow the QR code. If you have ideas for integrating the generator into your own projects, we will be happy to help and answer your questions. Let's use the generator together.